All right, welcome back. We are COMP2142. That's Game Artificial Intelligence 1 in the winter 2026 semester at Georgian, and it is week 2, part 2 of our broadcast and recording. In the last part, we talked briefly about assignment 1A. That assignment 1A is due Friday, January 30th, 2026 at midnight, and this is the same due date as the other two assignments that you've been given this semester so far. Each of these assignments is worth 15% of your final grade, and like I said, I highly recommend you work with somebody else on them, and you organize yourself because they're all going to be due around the same time, give or take. Again, we're approaching Global Game Jam, and I may move these a day or so just past Global Game Jam to get them done, but that's not going to give you a lot of time. My recommendation is Global Game Jam is on the 30th, and this assignment's due on the 30th. Don't wait until the last minute. There's just no way you can get everything done in one day, especially when you have 3 things that are due. So start doing them throughout the week, throughout weeks that I've been giving you. For example, I've given you your assignment 1 for Game 2004, which is your exterior systems assignment. You should already be working on that. You don't have to wait for me, to start designing what that looks like, right? Multiplayer is different. We talked about that yesterday for a brief time. But there are parts even in multiplayer that you can start off on, like for example the level design part that I've given you for multiplayer. And for this one, that's the one that you're going to have to work with me on week over week. So if anyone's going to get a little bit of an extension, it's going to be probably this one, okay? But we'll see how that goes as we approach the end of the month, which isn't far away. All right, so that is the stuff that we've talked about so far. This week we're talking about AI movement in games, an intro to steering behaviors, kinematic movement, seek, flee, arrive, and wander, what those things are, division schemes, and the seek algorithm we'll be talking in more detail. One thing that, oh yes, I'm so sorry. One thing, here is this, and here's this, there you go. One thing that we want to talk about as well today, and I'm just going to get into this, is your starter project. So I recommend you start downloading it now. It's not very big, as just like I said for the other one. This one has very few assets because we don't need a lot of assets for this one. It's not an asset thing. It's more of an algorithm thing. If you go up on Blackboard, you will see this link, right? So again, I'm just going to edit this link and also put it in your chat here, but you can get it right on Blackboard if you want. Here it is. So here it is in the chat. So when you download this project, please retarget for 5.5. Make sure you do that. And again, it's due 2 short weeks from now on Friday the 30th. We will have class most likely on Friday the 30th, even though Global Game Jam is starting on that week. Friday the 30th is also supposed to be a remote week, so most likely I will be hosting the class in person that week. And for some people who can't make it because they've planned their weeks around being remote, I will also broadcast on Zoom at the same time that I'm in this class on the 30th. So again, if we look at our schedule, because Global Game Jam is right around week 4, only a couple weeks away, then the important thing for us to do instead of it being remote for that particular Friday is be in person. So that's what I'm going to be doing. And we've got some remote days already, that we've done this week because of snow and all that stuff. So it's fine if we just move some of this stuff in person other than being remote. So that's kind of the plan as we move closer to Global Game Jam. And again, if you haven't had a chance to sign up, please do so. I think it's going to be a lot of fun. And I think there's pizza being provided. Yeah, I'm pretty sure. You get some food and drink and stuff like that. Movement in games. Last week we talked about what AI was, and this week what I want to talk about is movement. Again, we're going back to this model. All right, so back to the model, and what we want to think about is where movement sits inside of our model. And when we say model, like, imagine if I'm drawing the architecture of your own game engine. You're building your own game engine for AI, right? Then you're going to build something that looks like this, like in terms of in your head, like at least on paper, you might have to design it simply like this. So again, decision making sits on top of movement. So before we can move, we need to make decisions on where we're going, right? But we can't move anywhere unless we have movement algorithms. So that's why we're doing it kind of in a reverse order, right? As opposed to doing decision making first, right? Again, notice this world interface. This world is giving input into the group AI strategy as well as to the character AI decision making and movement. That's what happens. And there's actually should be kind of a two-way arrow here, because the AI can affect the world, and then the world can affect the AI, back kind of in almost like a positive feedback loop. So really what we want to think about is movement algorithms that don't really require a lot of complex decision making. You want to move a player across a screen in some way, and you want to be able to control them. Let's assume for a second that nav mesh in Unreal Engine doesn't exist. You don't have access to it, or you don't have, or maybe you're not even using Unreal Engine. You're using some other engine of your own, and you don't have a nav mesh, but you want to be able to move your enemies around in a very fairly controlled fashion. So what we're going to be doing is creating this autonomous character or an AI agent that's kind of moved to the target after the decision's been made. So whatever that is, you want to seek to a target. And by the way, the AI agent can even be a heat-seeking missile. That could also be something. We're actually seeking towards the target without any kind of pathfinding algorithm. Here, we're not talking about pathfinding. We're simply talking about movement from one node to the other. So when we think about this, the one thing that we have is this idea of a current position and a future position. I have my current position where my node, where my pawn is, let's say, the pawn that's going to move. And then I'm going to have some future position that it's going to be in, which is pretty simple to think about, right? I'm probably going to make some kind of, or give it a movement request. I'm going to say it's time to move, and almost like move to, some kind of move to function that I'm going to give it, right? And that move to request, it's going to start off, if it starts off with a 0 velocity, then it's going to get a direction to start moving. It's going to follow some kind of movement algorithm, as an example, and then it's going to move in the direction that it's supposed to go. It might get another movement request to change its direction, as an example, to follow a player or do something else. And that's kind of like more the dynamic nature of how this is all going to work. So again, what we really need is this idea of position. And the other thing that we have to think about is the game state. So what's happening currently in the game, as well as the level geometry. Is it flat like I'm giving you here, or is the level, does it have mountains that you're going to go through or whatever? Or are you in a game where you're playing a three-dimensional game? Here, with our course for game AI1, it's simply a flat two-dimensional plane. Even though I'm using three-dimensional characters that you'll see, I'm just treating it as 2 dimensions. And for this, the reason why we're doing it this way is to make it easy for you to understand and not to worry about the Z direction. Because once you start worrying about that third thing, that third component, it becomes that much more difficult to figure out. Okay? So again, there are generally two types of AI movements: a kinematic movement and a dynamic movement. And we'll talk about the differences between those two. So kinematic movements in general, we consider things like positions, velocities, and orientations. Where you're looking, what's my velocity, and where my starting position is. Characteristics might be deterministic paths. I have a path that I'm going to follow. There's no physics involved. I don't care about physics at all. I have direct control. And the good thing about that is movement in a kinematic movement scenario is very predictable, because I know exactly what the movement's going to look like. Okay, I'm not pushing my pawn around. For example, when you built something in Unity last year, you may have been using physics to move your game object around, as an example. Like you press the D key, and when you're moving towards the right, as an example, it's not repositioning. That's not what you're doing, and you may have not done that in Unity. What you probably would have done is push your pawn or your object to the right, and then it would kind of slow down due to physics or something like that. That's possibly what you did when you made your platformers and other things that you did last year. But this is different. This is actually more of a predictable movement scenario where you're repositioning your pawn from one location to the other. Dynamic movement, on the other hand, takes other factors into consideration. For example, instead of just talking about velocity, now we're talking about acceleration. We care about forces and masses. We kind of use the whole physics engine to help us out. So generally, dynamic movement is physics driven, right? So I push a pawn in a direction, as opposed to I relocate a pawn from one place to the other, like what we're doing now. Okay, I'm not going to be using physics in this course, because again, it's just going to be less predictable, like it says here, and much more difficult to figure out what's going to happen. One thing we should talk about is this idea of dimensional space. Like, we have a reference axis that we're using. For us right now, we're using a Z up axis. In Unity, it's not Z up, it's Y up, right? Luckily, Unreal and Blender are kind of aligned in the way that their coordinate system is kind of in the same functionality. But really what we're talking about when we say, when we're moving things around, is we're using this idea of turning in radians, right? Because remember, computers use radians for any kind of angle calculations. One thing that you should know, and you probably learned that last year, is that we use trigonometry a lot, to calculate things like x and y coordinates. So things like sine and cosine and tangent, to calculate the angle of incidence when I want to go from A to B. That's what we're going to do with, when we're changing things around. We're going to do that again this semester when we're thinking about how to change direction, and this idea of rotation rate, which is different than sometimes then it's not quite angular acceleration, because we're not going to use acceleration. We're going to use we're not going to use dynamic movement here at all. So one thing we talked about is this idea of a unit vector, right? So when I want to, this is a little bit of a review for you. If you think about what the unit vector is, it's the direction from start to endpoint, right? And the way we calculate that is we take the end vector, whatever that is, and we subtract it from the start vector. So it's just literally vector subtraction. When we do that subtraction, we're going to get the length of the two vectors from A to B. So for example, if I was going to draw it out for you here, right? So let's just do that with some simple shapes. Let's suppose you have a location here in space, and there's another location over here, right? So there's two vectors. Here's these two vectors. And I want to find the direction from this one, and let's just use this as the green. Green will be the start node, and we'll change the fill to red, meaning that's the end node or the goal node as an example. So what I really want to do here, if you think about it, is I want to traverse from here to there. That's what I want to do, okay? So in order for me to first do that, I need to know the direction I want to go in. And to figure out the direction between this position and this position, remember, positions are just expressed as vectors relative to the axis, right? So remember, and again, hopefully you remember some of this stuff. If you don't, it's totally fine. I'm going to review it with you, but let's suppose I have these two axes. So I have the, let's do it like this. I have the y-axis here. This is the y-axis. And I also have the x-axis, right? And let's suppose this is the origin, right? So here, this is the origin at 0, 0, right, as an example. And again, I don't want to bog you down with too much math, but hey, we need to do some of this stuff at some point, and so don't be afraid of it. So let's say, for example, this is the origin, so this is 0, 0. So move this up here so we can think about me drawing on the board here. This is kind of my whiteboard. Then we have this object at a specific location. I know, right? We have this object at a specific location, and it's relative to the origin. That's what it is. So let's just give it a number so we can understand how this works. Again, this is all review for you, so please bear with me. So let's suppose each of these units is 1, and I'm going to try and be as organized as I can when I make my little number line here. Again, you can do the same thing, with yourself if you want to, you know, kind of try this out, right? And I'm just going to say something like this. And we're going to keep on counting. So these are all units on the number line. I'm just randomly putting these things down as organized and as equal by eye, as if I was drawing on the board as an example, as I can. So bear with me. It doesn't have to be super accurate, okay? Just should be somewhat proportional. And the same thing goes with, so this is the x-axis again, and let's just do the y-axis the same way. We'll try and keep as proportional as we can here as we move and draw this number line, right? There we go. So we have some units here, whatever it's going to be. Oops. And let's suppose here, using this coordinate system that I've roughly drafted up, that the green square is 1, 2, 3, 4, 5, let's say 6 units, just to make it even. Let's move it, actually move it right to the 6 units right there. So that's what it is. So it's the coordinate for this one is 6. Is 6. Here it is, the cube, the square. So it's 6. And then, you know what? It looks like 6, 1 to me. Right? How about that? 6, 1. And then, for people who don't remember or don't understand what I'm doing, I'm hoping you will figure it out eventually. And this one will be 1, 2, so 7, 8, 9, 10. This will be 10. And I don't know, 1, 2, 3, 4, 5, 6. Let's say this is 7, right? Something like 7, or maybe maybe it'll be 6. How about this? 10, 6. Doesn't matter. All right, so I want to find the distance between the two things. And for you lovely people, how would you do it? How would I find the distance between the green square and the red square? What's the way to do this? Does anyone remember how to do that? Pythagorean theorem, very good. So what I would do then is, in order for me to use Pythagorean theorem, I need two things, right? I need a right angle triangle, right? So that's one thing that I need. So here is, you know, one of the axes on the triangle, and the other one is this one. So there's my right angle triangle. Let's suppose I'm doing this one. This is the right angle right here, right? So I have the hypotenuse. That's the angle that I want, right? And I have this, knowing that that is a right angle. So let's just put that as a right angle. There we go. Right, that's my right angle right there. And just make that like one of those. So now that I have this, you know, this idea, how many squares is it from here to there and from here to there? I have to use Pythagorean theorem. I know that the x-axis, the distance on the x-axis from one to the other is 1, 2, 3, 4. The distance between 10 and 6 is 4. So again, the formula is, if I was to draw this out, let's see if I can actually do this with any kind of certainty here. And yeah, here we go. So let's put the formula way up here so I have room. So I want to do x2 minus x1 squared, right, to the power of 2. That's what I want to do in the power. I'll use these the caret operator there, the power of 2, right? Plus, and then y2 minus y1 to the power of 2. Right, that's what I'm kind of doing. And all of that is put inside square root. So I can do square root of all that stuff right there. That's kind of the formula that we're looking for, okay? And that's going to give us, you know, kind of the things that we want. So if I look at x2, so this is 10 minus 6, right? So that is going to translate into, I'll just copy that formula for a second just to make it easier for you to see what I'm doing. So we'll put that over here. 10 minus 6 is 4, right? 4 squared is 16, so we can replace this with 16, right? And then y2 minus y1, y2 is 6, y1 is 1, 6 minus 1 is 5, that kind of worked out. And 5 to the power of 2, 5 times 5 is 25, so that's what we have there, 25. And so we have 16 and 25, and if we add them together, that's 35 41. Am I right? 35 and 6. Yeah, 41. So square root of 41. And if we, that's a weird number. So if I pull up my calculator and if I say, 41 square root is around 6.40312, blah, blah, blah. So the distance between this from the green square to the red square is approximately 6.4 units. Okay, that's the distance. So let's just do that. Hopefully you understood that. 6.4 units, right? That's what that is, the distance. And once we know one thing, once we know the distance, between one thing and another thing, we also know this distance here too, right? We know that this is the distance is 10 minus 6. So this is 4, right? So that's what this distance is, right? We know that that is 4, right? And we also know that that is 5, right? Or sorry, did I say 5? 6 minus 1. Yeah. Well, it doesn't look like 5, but it is 5. Okay. Again, it's not proportional the way I drew it, but that's what it kind of looks like. It's 4 units this way and 5 units that way. That's what we said. So it's a 3, 4, 5 triangle. It's a magic triangle that I've kind of drawn for you, right? Magic triangles. There's a bunch of them, in math. There's a 1, 1, root 2 type of triangle and other kinds of magic triangles, if you will. That's what they are. But this is kind of a simple one to figure out. If it's 4 and 5, this has to be 3 equivalent, right? So a 3, 4, 5 triangle equivalent. So that's kind of what it is. But anyways, am I right here? 6 minus 1. Yeah. So 4 squared, 16, 25 is 30, 41, right? I'll be okay. But anyway, so that's kind of what it looks like. That's kind of the relationship. And once we have one angle and we have, we can solve the triangle because we also know the distances and all that kind of stuff, right? So now that we have the information about it, we don't care about if I want to know the direction. Now that's a different thing. I have the vector for the red square and have the vector for the green square. And if I want to find the direction, I don't need this whole distance. I don't need this whole thing here, right? All I need is the unit vector, which is just like this. It's just a length of 1, which is like that. Okay, that's all I need. I need kind of something that points towards this, but is not the entire magnitude. I don't need this whole thing, okay? Because that's what you'd be drawing. And the way to do this would be subtraction. So I would do vector subtraction. So 10, 6 minus 6, 1, right? That's what I would do. So I would do that first. And it would give me this, kind of magnitude. That's what it would give me. And then what I want to do is I want to normalize this. In order for me to get the unit vector, I take the difference between the two vectors and then normalize. Does anyone remember what normalization is? And how do we figure that out? How do we figure normalization? Anybody? Yes, that's correct. So, but for each component, right, is what we want. So if I think about this as an example, and if I do some vector math here, so let's just do that. So we'll say this and minus this, so 10 minus 6, and kind of thing, and 6, we made a very simple vector. 10 minus 6 is 4, and a 6 minus 1, 6 minus 1 is 5, like we said before, a 4, 5, object, that's what it is. Well, I can take each one of these things, and I know the vector length, which is 6.4 now. That's the length of the vector. We just calculated that with Pythagorean theorem. For me to normalize this, I would simply just divide this whole vector by the vector length, which means I would take 4 and divide that by 6.4, and I would take 5 and I would divide that by 6.4, right? And then once you have that, you'll have some kind of ratio between the two. Okay, makes sense? And that's how it works out to be. That's the, kind of like, and if I was to take those, let's just get that number. So let's get that number here. So if I say something like 4 divided by 6.4, just to give you an example of numbers, you're going to get some kind of number between 0 and 1, 6.25. And then we'll do the same thing with 5 divided by 6.4. Again, approximate numbers, 7.81. Let's say 7.8. Sure, 7.81. 7.12. How about that? Because we want to be the same. 7.812. Did I do that right? 0.7812. Haha. Too much. It was 7. I was like, come on, Tom, what's wrong with you? So that's kind of what you're looking at. That's the unit vector. Notice that the unit vector goes from 0 to 1. Okay, and it basically tells you the ratio or the proportion between you know, the y component and the x component. That's all it is, a proportion, right? And then all we need to do is, once we have this direction, so we're going to get the unit vector. Once we have the unit vector, then all I have to do is multiply each of these components by the speed that I want to go in, and then I will move in that direction, right? Because when I multiply by the speed, I'm going to go to the next vector. I can take, this is the direction, and I can take my initial you know, position. Let's say I'm moving from green to red, right? I can take my initial position, which is 6,1, and add in a factor of this, you know, kind of direction. This is the direction, and let's just say that over here. So we'll kind of, you know, one of these. So here's the direction. And once we have the direction, right, then all we need to do is add this to the initial position and then multiply by the speed, and we're going to go in that direction the entire time. Does that make sense? So it's kind of like what we're doing the entire time when we're moving. If I want to change my orientation, where I'm looking, then I'm going to use this idea of sine over cosine. So I would need to know the angles here, the angle here and the angle here. And again, we can figure this out by using trig. Is this familiar? This kind of idea? Is this thing kind of familiar to some of you? Anyone lost? Hopefully you're not lost, because you need to know some of the stuff to do any kind of movement in AI, and or even make your own physics engine eventually as well. So again, what we're talking about here is the unit vector, right? And we're moving in a specific direction, and we're doing that through steering behaviors. Let's talk about the father of steering behaviors. It's this guy here, Craig Reynolds. 1999, he wrote a paper called Steering Behaviors, right? It's actually out there today. And it's basically a bunch of techniques on how to control the movement of an autonomous agent or AI, right, from one location to the other, right? And the core idea behind this steering behaviors paper is that you want to compute a force that moves an entity or an autonomous agent, right, and you know, kind of in a desired direction based on its current velocity, the target position, and or the direction. Okay, that's what we're really doing. So if you actually look up steering behaviors, let's just look that up together. So if I did something like steering behaviors, and we say something like Craig Reynolds, there it is, then you'll be able to find the paper. So here it is. Here's the paper on steering behaviors. I highly recommend you take a read. It's not necessarily easy reading. I'm not going to tell you that that's the truth, right? I wonder if it's even going to download anymore. It looks like that one didn't. I didn't like that one. Let's see if this one's better. That one's better. There we go. There we go. Steering Behaviors for Autonomous Characters by Craig Reynolds. So that's the one that you want to use. Try this one if you want to try and access this one. And so the online version is here, and I believe it's a PDF from the GDC Vault, right, 1999. And really what he talks about here, yeah, see, they probably trounced it. It's too bad. Every year it's, you know, that's the one thing about the web. It's not the most reliable source. Let's see if I can actually find Steering Behaviors paper. Let's see if we can actually find that thing. Here's the PDF. Probably won't be able to do it, but how about this one? No, that's someone's presentation on steering behaviors. But anyways, if you take a look at it, it's out there. It used to be out there a little bit more than it is now. Clearly, it's gone away. I know, right? But if you can find the paper, and I'll see if I can get it for you. But basically what it is I've kind of consolidated it down for you anyway, is there are several steering behaviors that he talks about. And he discusses a bunch of stuff around the steering behaviors themselves. So he talks about seek, which directs the entity towards the target position. Flee makes the entity go the opposite direction. Arrive, wander, pursuit, evade, obstacle avoidance, as well as path following. So those are all the things that he talked about and more. Okay. So again, we're thinking about it from a kinematic perspective. So we're not taking into account any acceleration. So we're not going to speed up necessarily and slow down. We're going to have the same velocity the entire time. Can anyone tell me the difference between velocity and speed from a physics perspective? Does anyone remember that? So Griffin, velocity has a direction, right? And speed, we don't care about the direction of speed. So velocity, I always liken it to this idea of the displacement. How much displacement is there from the origin? If we have displacement from the origin, we have velocity, right? If we kind of leave the origin and come back, velocity is 0. That's the way you think about it, okay? Because really what we're looking at is not just distance, but also direction, like Griffin is talking about from a physics perspective. So acceleration then is velocity over time, right? That's what it is. And a change in velocity over time is acceleration. And when we say change, now my mind is thinking about calculus. The rate of change of velocity over time. Calculus, right? Acceleration. And acceleration can be expressed as positive or negative. So we wouldn't say negative acceleration, but we might say deceleration, which is something that we use. But for the most part, it's the rate of change of velocity over time. That's what we're talking about. Kinematics doesn't care about that. All we care about is smooth movement, a fixed movement with no physics involved, from one time interval to the next. That's what we're trying to do here. So you can clearly see if I want to talk about linear velocity, if I'm talking about velocity, it's the displacement over time. That's what that is. And that gives me, that. You can also break this down from a displacement, which is, r theta over t, right? Where theta is the direction that we're moving in, and r is the displacement. So sometimes we also just, think about things like angular velocity. So there's linear velocity where I'm moving in a straight line, and angular velocity when I'm changing direction. And angular velocity is how many thetas, how much of an angle do I change over time. So the faster I can change my direction, that's my angular velocity, right? And then velocity over time is what we're talking about, or change in angle over time. Again, this is expressed in radians. So one thing that when we move, we want to think about, even though we're moving positions, changing positions, we want to also keep in mind that our pawn in Unreal Engine is going to have an independent facing. I could be facing one direction and moving in another. Imagine you're on a nice field. This is a beautiful time to think about it too, because it's really cold outside. I think today was -20, and the field is of ice, and you're on boots, like flat boots. You don't have a lot of tread on your boots, right? But you have good balance. You're an athlete. Okay, that's what we're talking about right now. I'm picturing this thing with you guys, and you race onto the ice and you skid. You kind of move, kind of across the ice. You could skid sideways, right? So your facing would be independent of your direction, right? And that's true in real life, and it can also be true in games as well. I don't necessarily have to move in the direction that I'm looking, right? So those two things may be independent. Most often, when it comes to things like missiles, tracking, other things, autonomous agents, we move in the direction that we're looking, right? Typically. But in the case of a tank has a tank body, and then you might have a turret. So the turret might be looking in one direction, the tank might be going in another direction. But the tank body's still going to go in the direction it's quote unquote facing, right? But you don't have to. Autonomous agents don't have to, it doesn't have to be coupled together. It could be decoupled. Your direction and your movement, or your facing and your direction could be totally different. But what we want to do is kind of create this illusion of, kind of turning towards the direction we're moving. So let's suppose this is frame 1. where our object is moving kind of here, and then what I want to do is slowly, every frame, change my orientation for me to move in the direction that we want to go. All right, so this is kind of what we want, and this is what I'm looking for from you, right, for assignment number 1. I don't necessarily want to move, like if I'm looking this way and then I move down that way. So what I mean by that is, imagine if, I'm just going to cut this out here. Here's my thing here. Yeah, I even got my arrow. Let's try that again. Here, I'll cut it out. Let's try that again. So this, there. All right. So let's say this is my, my autonomous agent, and I want to move from the top left corner of my screen to the bottom left corner. I'm not going to do this. Okay, that doesn't make sense, right? What this graphic is telling me is, frame 1, I'm going to be here, and then frame 2, what I want to do is I want to slightly change direction, right? So I'm going to do this. So frame 1, I'm going to be probably up here, and then frame 3, and then frame 4, and then frame 5. You get the picture, right? And then frame 6, you're going to move this direction, and then frame 7, you're going to move kind of in down there, and then keep going slowly, one step at a time, until you're pointing in the direction that you want to move, and then you're going to continue to move there frame over frame until you get to where you're going to go, your destination. And that movement across the screen is what we're talking about when we're looking at, even though I might be moving in a different direction, I want to move in the direction that I'm facing. Okay? If that makes sense. So we can look at, when it comes to moving, right, and I want to update my position, I could use the, there's a kinematic equation that we can use, which is P naught T plus V naught T plus 1/2 AT squared. And when I say P naught, V naught, it's the initial position plus the initial velocity plus 1/2 acceleration squared, and you've got this really cool little curve to move from A to B. Actually, that formula gives you an anabolic, kind of like a curve that looks very nice, right? And so, for example, if I'm kind of firing a missile, right, or some kind of projectile, and we're talking about projectile motion here, then it's going to follow this parabola. So it's parabolic motion that we're talking about, and this is something that can help you. Typically, when we look at time in physics, we multiply it by time, and then here we're multiplying by time. It's because it's t squared. A lot of times what we do here from a computer perspective is we don't do this t squared stuff. It's too much a lot of times. So what we do is reduce the time interval a lot. Okay, and the reason why is because unless we're doing a pure simulation, then we wouldn't want to do this all the time. It'll end up being too crazy for our screens. You'll see what I mean later on. So again, so it's like it says here, the update time passed to this function is likely very small. And so what happens is because it's small and we're multiplying it by itself, it gets smaller and smaller. So because we're using some kind of frame interval, like each frame is like 0.00016 milliseconds, right? So because that's small, or 16 milliseconds is what I mean. For every 16 milliseconds, if I multiply milliseconds by milliseconds, I actually get a lower number, like 0.0000, right? So we don't want to do that instead. So we kind of like usually we remove the time function altogether and create almost like another way of doing things. We remove these terms. So let's talk about the two algorithms that are very similar, which are kinematic seek and fleet. All right. So here, this is a great little diagram. So imagine here's the target, and here is you. This is let's suppose this is the seeker, or we can also call this the start pawn, if you will. So the start pawn has a specific velocity, and it also has a desired, a specific direction. Remember, velocity has direction involved with it. And notice that the velocity is this whole line. That's how fast it's moving, right, as an example. So this is the initial velocity, and this is the desired velocity. We want to go into this direction here, right? So again, what it creates is this parabolic curve, right? So from the initial position and the initial direction to the final position and the final direction. This is kind of what we want to do, right? And so again, like what I said before, kinematic seek, what it does is it takes the target position minus the agent position, where you started off, and then you get the direction, and this direction needs to be normalized. And then for flee, it's the opposite. You take the agent position minus the target position, right? So you subtract it the other way around, and then it inverts the vector, the unit vector, so it points directly, diametrically differently from where it was pointing before, which is pretty cool. So that's really seek and flee in a nutshell, right? And this parabolic curve is the kind of curve that we want to go in. So it's not going to go directly in this direction. It's not going to snap to that direction and go in that way. Instead, what it's going to do is going to slowly march around, and then hopefully get that way. Really depending on the velocity, the angular velocity of your object. Just like I showed you earlier with that project, the more you turn we just call this turn rate. If I increase my turn rate, so instead of only moving at 30 degrees, I can move at 90 degrees or 180 degrees, then I can snap to that other direction really quickly, and I don't have this parabolic curve, because I can just like go in one frame, I can just like change my direction. That's not realistic, right? Realistically, people don't move that way, and neither do objects, right? They kind of take that long way. They have a turn rate. Cars, planes, spaceships, whatever, right? Missiles, and also particle systems. Okay, so that's kind of how they move in this parabolic path. Kinematic arrive is different. Like I said, notice that it has the same rate of speed or velocity here. It's changing orientation one frame at a time, but then when it comes to a certain threshold, it starts to slow down. It's not deceleration. I don't want you to think about that. I'm just cutting the speed down. That's all I'm doing. Remember, because deceleration is a physics thing. What we're doing is reducing speed. We're cutting speed down at a certain threshold, and we keep on reducing that every interval until we stop at 0. Okay, so that's what happens. So the goal of the arrive algorithm is your start pawn lands right on top of the goal pawn and stops. Again, this is all a factor of your turn rate and your rate of speed. The more your rate of speed is, so if this vector was a lot longer, as an example, you're going much quicker. Or, for example, if your angle of attack here, like right now, you can see it's kind of this vector is kind of pointing in the direction this area here, because it's going here. But what if my vector wasn't like that at all, right? What if my angle of attack was this way? Okay, it was kind of in a different direction. Well, clearly I'm not going to do the same parabolic path. It's going to go here, and it's going to turn around and come back this way. And depending on my turn rate, I may not hit that right away. I may keep on turning around and around and around and slowing down until I stop on that area. But it might take some time, almost like a little corkscrew. Okay, that's what that path usually takes. So, kinematic seek, it's used by to chase an autonomous character, but we do it at full speed the entire time. Kinematic arrive, it kind of has an area. Notice that there's like not just the target, but there's like almost a little radius that's around the target itself. And that little radius is where we start to slow down, right? So that's what that is. Wander. So I want to emulate what it's like to walk around, as an example. Guards, sentries, those kind of things. They don't walk in straight lines. Like what we did last semester with our AI, and it kind of walked from one waypoint to the other waypoint in a straight line. That's not realistic. People don't walk like that, right? They slow down, they speed up, they look around, they pause, right, when they're walking around. Especially when they're, kind of patrolling. They might have their weapon in their hand, they look around, and they'll stop for a second, as an example, and they'll do different things. People, to be more realistic, wander. We don't walk in a straight line. If you actually, watch yourself, if you look at your footprints in the snow, right, when you're walking, depending on how straight your feet are and your legs, you might be walking like a duck, right? That's what it might look like behind you. And you might see like a path that kind of zigzags, because people don't walk completely in a straight line. We're not robots. Even robots don't walk like that. We tend to wander. And the way to simulate wandering is to have this random steering. So think about, instead of having a direction, a fixed direction, we have a direction in a particular circle, right? And the radius of the circle is what we use for potential points of direction, right? So what we're doing is every frame is we we go in a particular direction, and then we go towards that direction, that frame, and we walk in that direction for a few frames. One thing that we want to try and do here in this course is we don't want jittery movement. So we don't want to kind of change direction every single frame, because it looks like you're going to be wacky. It'll be look like your actor or whatever is going to go back and forth, like, or flutter, if you will. And we don't want that twitchy kind of movement. So what we do instead is we say we're going to walk in this direction for X number of frames, or this length of time, and then we're going to be able to move and do something else. Okay? And that's going to create more of a realistic wander algorithm. Now, we're not going to be doing wander together, but I think it's a worthwhile thing to incorporate if you want realistic movement, in your games, especially when it comes to patrolling and that kind of stuff. A wandering kind of, AI, as opposed to an AI that's like going in a direction, a straight line. So those are the things that I want to talk about today, those four, right? So seek, flee, arrive, and wander, those four. And in order for us to do this, we want to think about moving across but using some kind of division scheme. So again, I want to move from point A to point B in a world. And I want to use steering behaviors in order for me to do this, right? And I can achieve this by dividing my world up or cutting it up into some kind of quadrants. Like we do it all the time in Unreal Engine. You saw on Wednesday when we got together, we actually had a bunch of these quads that we were using inside of our landscape. And what we do is we cut that landscape up more and more and more. We divide it up into smaller pieces, and then we give the illusion of changing the height of different vertices, kind of inside that quad to create that landscape-like effect, right? So I liken it to using something like in Blender, right? When we think about a division scheme, I'm going to bring up Blender here for a second, and this is just simply for demonstration purposes. I don't need you to do it. I just want you just to chill for a bit. So imagine if I've got instead of a cube here, I'm just going to get rid of everything in Blender. So here's my cube. Let's suppose instead I have I'm just going to add in a plane. So here's my plane. And I want to do kind of this landscape idea here. Well, if I just have a plane, I only have 4 points, right? And 1 face and 4 edges. That's all I have. Remember, any geometry that we're looking at in a three-dimensional space is made up of vertices, edges, and faces. That's pretty much what it is, right? So if I go into edit mode here, as an example, I could cut this little plane up into small pieces. And before we do that, let's make it bigger. And we'll do this later on this semester as well. But let's suppose I want to scale this up, right, kind of equally. And I want to make it so that it takes up, like 10 little squares. Okay, so 5 on one side, 5 on the other. You can try and do this yourself too. You can see that the scale would be then just 5, right? 5 across each one. I'm just going to scale it up 5 times, right? And that's the scale for this particular square. And because I have 5 squares and 5 squares, if I go into edit mode, I can subdivide that. So I can go into subdivide it. And right now you can see that I've only subdivided it once. So basically what it does, it creates four squares out of 1 square. If I keep subdividing it though, you can see as I continue to do this, I get to the point where I can match the number of squares here inside of my grid on the outside with the number of squares inside of my my plane. So now you can see that I have kind of 10 by 10, 10 by 10. And this is not a lot of geometry. Okay, if you think about it. So if I was going to try and do something like sculpt this thing, right? I mean, you don't have a lot of control over how to sculpt it. Like even if I try to do that, if I sculpt it in Blender here, and let's say even if I increase the size of my brush, right? So here's the brush size, so I can move that brush size bigger. Here's my brush size. I can kind of do that in Blender as well, right? Because I have enough divisions where I have some things, and all I'm doing is literally displacing the vertices from one place to the other, right? And it's all based on the division scheme that I'm using, right? I'm taking an area and I'm cutting it up into a grid, And then once I have that, those grid squares, I can literally do any kind of traversal I want. I can modify each of the vertices. And if you think about each of the grid squares that I have right now here, all I've done is displaced, increase or decrease the Z value. I can decrease the Z value as well, right? If I go back into sculpt mode, I believe it's just the same thing. So I can decrease the Z value here, right, in different areas. There we go, by pressing the Control key. And then let's go back into what this looks like. So you can see this increase and decrease the Z axis of each of these vertices to create almost like this displacement map. That's kind of what we've been doing. We do that in, whether it's here in Blender or in Unreal Engine or in Unity or whatever, or your own engine one day, it's the same thing. But each of these things we have, it's a quad, right? It's a little division that we've created. The more divisions we have, the more accurate that we can control our world, right? So again, if I was to take this thing, let's further divide this even more. So if I take this and divide it again, subdivide, and I continue to add geometry, to this thing, let's just add another 9 or 10 divisions. You can see this becomes very dense, right? And then I have way more control when I get into doing something with my sculpting, right? So I can, instead of it being as rough as this, now I can create almost like mountainous regions and that kind of stuff here, just like we did when we were using the geometry inside of Unreal Engine. It's kind of the same thing, right? And the great thing about Blender is it has quite a few tools in terms of how to sculpt, as an example, or doing different things, right? So if you go to sculpting, you can decide on the kind of brush that you want to use, as an example, and a bunch of other stuff here. As we go forward, you can see that this is the standard brush down here, a draw brush. You can also do a crease, so you can kind of increase the crease there to make it more detailed, right? And for example, if I want to create almost like this idea of a river that goes through my geometry, I can do that, right? You can do those kind of things, right? And then you can crease it that way. You can also increase other things here. You can inflate and deflate areas, and I can decrease my brush size and all that stuff. And it's literally, if you think about what I'm doing, right? All I'm doing is I'm displacing the vertices that I've created earlier, okay? This idea. And so you can create your geometry the way you like. Okay, does that make sense? So division schemes give us a lot of power, right? Whether we're doing it in 2 dimensions or in 3 dimensions, it allows us to, to kind of, look at the world. And all we've done here is we just added a lot of geometry, right, around this area. And the more geometry we add, the more control we have. The more geometry we have, the more vertices we have, the less performant our engine is, right? Because we have to deal with each specific vertex as a vector, right? And that's what it is. It's the same thing when we're making an organic model, right? As an example, that organic model has a bunch of vertices, and those vertices are around a specific bone. When the bone moves, we use kinematics, really, at the end of the day, to displace the vertices so that each of the vertices surrounding the bone, the flesh around the bone, follow the bone's movement, right? And that's kind of what we're doing as well. But everything that we do is, in 3-dimensional modeling and even in animation, is a kind of a part of a division scheme, if you think about it. Why am I talking about this? Because there's lots and lots of ways to do pathfinding, and there's lots and lots of ways of doing movement, right? We could use nodes. I could use a bunch of nodes, just like waypoints, like we did last semester, right? And we can move from one waypoint to the other, right? And we can have sparse waypoints when I want a character to move around them. The more waypoints we added, like we only added 4 waypoints or 3, we can add 15, 20, 100, and we can create a path, almost like a spline that a character might move, right? And we can do that with a nav mesh. But instead of relying on engine tools, we can also do it on our own. And this is kind of what we're going to be learning how to do in this first half of semester. So tile graphs are very common, right? They're more common. They were more common before, but definitely far from dead. Where we kind of subdivide a world into, a grid. So that's one thing we can do. Here's an example of Fortnite, right? The map from Fortnite way back, where we can kind of, that's what they did. They kind of subdivided this world and cut it up into squares, right? And underlying all this graphics is just a regular grid. So, and such a grid, we can, you can turn it into a tile-based graph. Each tile then, if you think about it, or square, right, is something that we want to move across. We want to move our AI agent across from one tile to the next. That's what we're doing. Think about a board game simulation, right, where we have a board game and I want to move my piece, my player from one board square to the next, right? And I want to be able to do that in that kind of fashion. That's what I want you guys to focus on this semester, especially in the first half. And I'm giving you these constraints because there's a great amount of learning from constraints. I've always been a believer in that, right? So if we constrain ourselves, we limit ourselves to what we can do, and we work within those confines, we find ourselves a little bit more creative than if we have no constraints at all, right? In fact, in no constraints, we a lot of times flounder and don't get things done, believe it or not. So let's think about this tile-based, world that we're gonna split things up. And again, use case scenarios are, square worlds like that we might do, splitting up into squares, or even hexagonal regions that we might use in things like civilization and that kind of stuff that we traverse, right? So this idea of tile graphs is a type of division scheme, right, where nodes in the graph are represented by tiles in the world, okay? So each cell or each node, right, we can interchange that language. We can say a cell is a node, right? The tile itself is a node, is a waypoint, okay? So what we're doing this semester is we're making a very dense graph, okay? Instead of making a very sparse graph like we did last semester, where we only had 4 waypoints, now we're going to have a lot more waypoints in there. And what that's going to do for us, because it's going to be so dense, is it's going to increase the complexity of how we're going to move from one node to the other, especially when it comes to pathfinding, because there's going to be many paths to the same, to that direction, the direction we're going. Each tile then is going to have a certain amount of neighbors, and there's going to be a relationship. Again, not necessarily right now, but there's going to be a relationship between one neighbor, or one tile, and the next, right? In the second half of semester, what we're going to do is we're going to create a mapping between one tile and the next tile and the tiles around it, right? And the reason why we want to do that, and we have that kind of movement, is to create, to decide which direction to go, which is the most efficient direction to go, as we do pathfinding by hand. Okay? So we have these links between tiles. One thing to note also, by the way, is when we move in a hexagonal, on a hexagonal map, right, we use 3-dimensional movement. So there's like X, Y, and Z, because there's actually, each hexagon has 6 faces, right? And I can move to the right in 3 directions, and to the left in 3 directions. But the X, Y, and Z means different things, okay? Look, almost like there's a column and a row, but there's also another kind of row. So, because there's there's 3 lines, right, kind of involved in a hexagonal movement, and there's a different kind of coordinate system that we'll be using in from that perspective, as opposed to using something like a square tiles. An example of that would be this project I've been working on lately, and I'm just going to go to my project here for a second. And let's just get into that 1 second, so I'll show you that. It's been a long time coming. It's not, believe it, when you first look at it, it's not that, may not be that impressive, but what we have is this idea of a galactic map, right? The galactic map is made in WebGL, okay, as an example. And let's suppose I want to, calculate the shortest distance between 2 star systems on the galactic map, right? So I want to go here from Veracal, as an example, to Perun, right? So how do I do that? I can try and find the path between here and here. And what it'll do is it'll map the shortest path across, the galactic map. Now I want to point out something for you here. And we're going to talk about pathfinding later on this semester. But if you notice this, as an example, each hexagon has 3 faces, right? It's not the same as going across, a square. You're going to try and figure out the coordinate system between one hexagon and the next. The neighbors each hexagon has, as an example, there's 6 neighbors per hexagon, right? And that's all it has. So the beautiful thing about hexagonal movement is it gives you some more natural movement across the surface as opposed to using squares. Squares, because you going a diagonal across a square is actually cheating in some ways. It's you can, if you go from one square to the other, you're actually going faster in the diagonal than you would be across right, left, up or down, right? So whereas from a hexagonal perspective, each neighbor, as an example, is equidistant. Okay. So that is something we're going to be talking about when we're creating our grid as we go forward. Let's go into our project right now and discuss that project. So I've downloaded my project, and again, you can download this from Blackboard. And I'm going to stop in a second, I swear. But I want to talk about the project setup just for a bit. So here's week 2. I've called it week 2. But again, I've gone into Blackboard and I downloaded the starter project, and I've extracted it. I've also added in a gitignore and getAttributes file of my own, as opposed to generating it here. So again, you can get that getAttributes and gitignore file. I've given it to you already, but if you need them, then I'll just put them up on your chat again one more time. So I'm going to copy these and just dump it into the chat. So those 2 files you need, because when you put it up on DevOps, you're going to need a gitignore file and a getAttributes file. So this is my project, and the project is SB starter project. So SB stands for steering behaviors. Yeah, there's a reason for why it says SB, right? When we launch it, I'm going to launch the project for a second, and I'm going to show it to you. This is unlike what we had before. So the project itself comes with some things. You get something out of it, okay? It's not empty. And however, one thing that you're going to notice is that it has very few assets, and more like the least amount of assets that you've seen so far, okay? You might see the project when you're first downloading it, and it might look like this, okay? As an example, or you might see it from a perspective like this, okay? And this is not the correct orientation for you to look at the project. What I want you to do instead is I want you to change that from a perspective. I want you to go from top-down approach and stay lit, my friends. Stay lit, like Connor likes to say, okay? Stay lit. And so now what you're doing is you're looking at a grid. All I've done to create the grid that I've done here, there's no special thing that I've done here. I literally have taken a floor, so there's the floor itself, and I've resized the floor so that it is exactly 40 squares by 40 squares. So you can see here, if you count the squares in the top and the bottom, using just the material that comes with the floor. It's floor material, right? So if you actually look at the floor itself, you can see that it's just using a proc grid. So that's a procedural generated grid. That's what that is. If we double click on the material instance here, you can see that it has a grid that's formed on it. And a better way to look at this would actually be to look at it as a flat plane. There you go. All right, so that's kind of what you're looking at there. And so there are some controls that you can put on the grid. For example, the grid properties. You can change the tint of the grid and a bunch of other stuff that you can change here. By looking at things like the checker color, you can change the colors of the grid and all this kind of stuff. It's all built into the material. Okay, so that's what we're doing. That's how it's been generated, and I haven't really done much else. Just made the grid for you and everything else. And once the grid has been made, whenever this thing feels like updating, there we go. Once the grid has been made, then when you play the game, let's try playing the game for a second. Hopefully you guys can do this. You notice that I can zoom in and I can zoom out, but I'm not really zooming in and zooming out. What am I really doing here? What am I doing with zooming in and zooming out? How am I doing that? There is no zoom in, zoom out, right? Also, notice that every time I move my mouse, right, I also change this little, location of a cell. Field of view, yeah. I'm really actually, what I'm doing instead is I'm literally moving my camera. I'm moving my camera back and, kind of field of view, I guess. I'm moving my camera back and forward. That's all I'm doing. So, so one thing to note is, to understand the project a little bit, is to go into our BP underscore grid character. So if we look at our grid character, there's already some code here for you. If I go to my viewport, the grid character has like nothing in it. It's empty, right? It has a mesh that's empty. It has a spring arm, and it has a camera. And if I was to look at the camera or the spring arm, you can see that instead of the spring arm being from the position on the side, the spring arm is positioned from the top. So it's a top-down kind of approach. That's what we're doing. Moving forward or backwards? Yeah, but actually I'm moving down towards the my character or back. So my middle mouse wheel is how I'm doing that. That's what's doing it. And when I scroll my middle mouse wheel forward, then I'm actually changing the distance of the spring arm of the camera from what it looks like all the way down. Right. So all I'm doing is zooming. That's how I'm performing the zoom in and zoom out. It's actually changing the position of the camera. Okay. And this code, if you look at it, I'm just going to kind of go through the project a little bit. Here are the actions. So you can see that there is the start cell. I have this right now, and the goal cell. And what I'm doing with those actions is a left click and a right click. So left click is the start cell, and right click is the goal cell, and zoom is another action. The input mapping context here. Notice that I've already mapped these for you. So I've started off with the mouse wheel axis is the zoom, and the S or the G keys select the cell that the mouse is pointing to. So how do I do that then? If I press play again, and if I zoom in, and if I left click on a cell, it gives me the coordinates of that particular cell in world space. Okay, so this cell over here is -150 and 550. It's the center of that cell. That's what we're pointing at. So the center region here. So no matter where I'm pointing to, and if I left click, it gives you this information. If I right click, it also gives you that information. That's the goal cell. And you notice that it gives you different things. Start cell, goal cell. So I already have that for you already. Okay, I already have that information. Okay. So I've kind of done some of the work for you, and I had to because it's a lot, right? So that's one thing. The next thing is when we look at our grid character, there are some things that are built in, some functionality that's built into the grid character itself. So let's look at the event graph. So the event graph starts off, and what we're doing here is we're getting our controller, and we're casting it to something called BP underscore grid controller, and we're saving a reference to it here inside of our blueprint. Okay, so let's take a look at the grid controller and see what that is. So if I go back to blueprints, we have our character, but we also have a grid controller. This is just a player controller. That's what I've done. If you notice, that's the class that I've created here, player controller. So player controller, this grid controller then, has a few things that are built into it, so you can get information from the grid. Okay. One thing is, in the event begin play, we do our mapping context here. Right. So we check to see if the enhanced local input local player subsystem, as an example, if our if everything is valid, and if it's valid, then what we do is we do the mapping context. So if the player controller has been instantiated, then that's when we do our mapping. Okay. One thing that we can do is we can show the mouse cursor if we want to, or hide it. So if I was to press play, you can see in the game that you can see the mouse cursor still. It doesn't disappear like it normally does when we play our game. So that's why the mouse cursor appears here. Okay. So that's why, because we've turned it on. All right. And in the event tick, right, what we're doing is we're using a little function that I wrote called get location under the cursor. Right. So if I look at get location under cursor, then what we're really doing is we're getting a hit result under the cursor by channel, and the channel we're using is the visibility channel. Okay, that's what we're doing. So what this does is it gives us a hit result, and I can take the hit result. So that means whatever the cursor is looking at, it's going to like cast down, almost like a ray cast, just like you would in Unity. Ray cast down from the cursor directly down across the Z-axis, right? and it's going to give you a hit, anything that it hits in the visibility channel that collides with the visibility channel. And if I open this up, you can see that this is just like any other raycast that we're doing, right? A trace, if you will. That's kind of what we're doing here. And then so the trace is, or raycast, is going to give us back a hit as well as the location, right? So location is something that we want to preserve. So whatever this location of is in world space, that's what it is. We're going to return this out of this function. So that's what get location under cursor does. It kind of, you know, translates whatever we're looking at as a location in space. But remember division schemes. We don't care about that exact location. We care about the closest grid location to that location in the center. That's what we really care about. So then the next thing that we want to do, if I go back to the event graph, I get that location under the cursor, and then I check to see if there's a hit. If I hit something, if I'm, you know, I'm actually intersecting with the floor, that's the hit. Then what I want to do is I want to take that location, that vector, and I want to snap it to the grid. So snap to grid is another function that I wrote. Again, it's not that difficult to understand, but really what's happening is I take that location and I break that location down, which is a vector, into its components, x, y, and z, right? And I save them. So I save the x and the y. I don't care about the z. I don't care where, you know, I'm, like how high I am from a mouse perspective. I don't care about that. All I care about is the x and y. So I ignore the z. We don't care about that. So then what I do is this current x and current y is the exact world coordinates that I want to use, right? But I want to take this idea of cell size. So cell size, what I've decided is that each cell is 100 units, right? That's what I've decided. You can make these cell sizes anything you want. I've made them 100 units because they align with the grid that is part of the map already, okay? That's where I came up with it. So the grid is 100 by 100. Each cell is 100 by 100. That's a cell size. So I take that current x and I divide it by the cell size, right? And then what I do is I do floor to integer 64. So I basically round down. That's what floor means. I round that number, whatever that floating point number is, into an integer. I convert it into a number. And then what I do is I multiply it back by cell size. So what I've done is I've truncated all the extra digits. I've removed, you know, a location like 35.6872 or whatever it's going to be from an x perspective, and now it becomes just 35.0. That's what I've done. When this cleans my coordinates, whatever it is on x and y where I'm pointing at with my mouse, it takes away of the rest of the thing. This is one way of doing it. Once I've done that and I've got a number here, so this is the, you know, kind of the clean number, the reduced to an integer number, then I add in an offset amount. And the offset amount that I figured out is 50. So basically what it is because each cell is 100 by 100, 50 is kind of the middle, right? It goes by, you know, kind of a radius, if you will, or an extent. The extent between from the middle of the cell to the edge of the cell is about 50 units, right? That's what the offset amount is, right? And it's usually half the size of the cell. I could have taken like cell size divided by 2 and made that the offset amount to be more, you know, again, scalable, but I decided not to. So I've done this. I've taken whatever that number is and I've offset it by the offset amount, and that becomes the x vertex, right? So that kind of like what that does for me is it creates a number that represents, you know, the x-axis. I do the same thing, the exact same thing for the y, and then once I have that x and y, I create a new vector, and that's what I'm returning out as the snapped location. Okay, so there's the actual location that I'm actually looking at with my mouse, and then there's the snapped location, the location that's closer, the closest number to 50 units every single time. I'm not going to go anything less than 50. That's what that offset is. Let me show you what I'm talking about here. So if I press play, and if I zoom in, and if I left click somewhere, notice that it's never anything less than 50. The smallest number is 50. That's what it's divided by, right? So if I go right down to the, you know, to the origin, if you will, so you can see here as I'm climbing up, I'm going higher, you know, here, and lower. Actually, these numbers are the opposite of what I'm looking at. It's actually y and x is what we're seeing here. That's weird. I don't know how I did that. Why I did it that way. But anyways, what it is it should be the other way around. Instead of it showing x and y here, I'm wondering where I printed that out. Wow. I must have been a little bit cuckoo when I did it. But if I travel to the left or to the right, let's say, then you're going to see here, between here and here is the origin, and between here and here is the origin. So the origin of the screen is right here. That is the origin of the world. I can't click at the 0, 0 mark because I can be minimum 50. Okay, 50 and 50. I can't go lower than that, right? And that's what this does too. It actually moves my cursor around. So even if I'm here, it snaps it to the nearest 50. That's what it does, okay? So that's the first part, snapping that thing that I'm moving around, okay? And that's what that grid controller does. The grid controller allows me to use snap to grid, and that's what I'm getting here. I'm getting a snapped grid location that comes out, and that's the cell location. And then I'm kind of just drawing a box, and that's the box that I'm drawing, which is this yellow box. Let's make it so it's not yellow anymore so you can see it a little better. I'm going to make it so it's red. Let's make it really red. And we can also increase the thickness. Let's make it a thickness of like 3. Here's a thickness of 3, and I made it red. And if I press play again, then you're going to see that now it's easier to see the box. That's kind of what I'm doing. So every time I move my cursor in real time, every frame, I'm moving, I'm redrawing, if you will, or I'm changing the location of my the box that I'm drawing here, this draw debug box, remember? And the duration is 0, so I'm continuously drawing this debug box as I move my cursor. Again, I'm not worried about performance here. I would normally not do this if it was from a game perspective where my mouse is moving across stuff. But again, there's only one object doing that, so it's not really that, it's not killing my performance all that much. Okay, but that's what it's doing. That's what the draw debugs does. So again, 2 parts. Get the location of the cursor and then snap it to grid. And then draw the box. I have some information here that I'm sharing from my grid controller. My grid controller gives us the vertex X and vertex Y, the cell size, the offset amount, the current X and current Y, and the cell location. All this kind of stuff are the things that I'm recording, but I'm only exposing the cell location, the thing that I'm actually looking at all the time. So we can always get the cell location from my cursor at any time. Okay, that's one thing to note from my little project here. So that's the grid controller. So that's what I get here. In event begin play, I get a reference to the grid controller, and then when I'm zooming, this is my zoom ortho camera. That's another little function I wrote for you guys. I take the camera, right, and I look at its ortho width, and every single time I change the value of my zoom, I actually like move my my middle mouse wheel, I multiply that by a -200 and then add on the ortho width, right, the orthographic width, right, which basically changes the, because I'm using an orthographic camera, so effectively I'm changing the field of view, if you want to talk about it that way. I am moving my camera around, but I'm clamping it between 750 and 10,000. So I'm not going to allow you to do it forever. There's going to be a limit to how close I can get and how far away I can get, and that's what that I return out the ortho width that I'm getting when I'm zooming in and out. So again, if I'm pressing play, and I can move in quite close, but this is the closest you're going to get. And if I move out, this is the farthest out you're going to get, like way over here. Okay, and if you don't like how far this is, if you think this is way too far out, you know, to see this this thing way over here, that's fine. Then we can change the distance. Instead of 10,000 or whatever it is, you can adjust the distance so it only takes up the screen. But that's really, in a nutshell, how the orthographic width is changed for this from the camera. Okay, so that's what this does, and this happens on zoom. The select start cell. Again, all I'm doing is I'm getting the grid controller and getting my cell location. That cell location is in X and Y coordinates, right? And then all I'm saying is let's append the cell location. I'm taking that cell location, and the start cell is something that I'm going to output to the string. Okay, so going back to my grid controller, one thing to note, because I know that there's a bit of an error in terms of the way I'm printing things out, and the reason why there's an error is because the X and Y coordinates that I'm saving, that's the cell location. The cell location is created by my X and Y coordinates, right? So again, if I look at the location under the cursor, I don't really get it here, right? I get it inside of the snap to grid function. Snap to grid function sets up my, my X and Y. Here's my vertex X and my vertex Y. And what I've done here is I've reversed some of the ways this is working, right? Because that's what the Y and X coordinates are. Here's my location, right? My location X and Y. And that's why I'm getting weird numbers, because what's happening is the screen should be actually rotated, if that makes sense. And we'll see that later on. I'll have to, it's correct. My orientation from my screen needs to be adjusted. Okay, so, but we know that whenever I use the start cell and the goal cell, all I'm doing is I'm getting the controller and I'm getting the cell location, whatever that cell location is, and then what I'm going to do is I'm just outputting that cell location when I'm left-clicking. Left-clicking, I'm just getting that cell location and outputting it. Right-clicking, I'm getting that cell location and outputting it. That's really, in a nutshell, what I'm doing. And you can tell that it's a problem because, look, here's the y-axis and here's the x-axis, right, as an example. And that is correct orientation, right? But the way to see this properly is when we are starting up our game, right? This may not be the way it's looking, right? And that's why it looks messed up. Because if I go back to, from a perspective, here's my perspective, it should be looking like this. Here's X and Y, right? And notice that X shouldn't be like this, right? There's X and Y, right? There's north and south. And the x-axis is, and the y-axis looks reversed. And this is because of my orientation of my character, right? If that makes sense. Right, so how should this be, should be made? It should be looking different than what this is right now. Also notice that it says west, east, south, north. So what we need to do is these two locations should be flipped relative to what we're looking at. So instead of this being the x-axis, it should be the y-axis, and this should be the x-axis here. Okay. Questions around this? All right, so we're sitting at 2:30. I want to take a short break, and when we come back, what I want to do from there is I want to do a little bit of coding with you, and that's why I've shared some of these PowerPoints. The next thing that I want to do after this is I want to start thinking of creating the grid with you. Even though we've made a grid that you can see, there is no logical grid that we want to keep track of. So before we either place any kind of pawns on the grid, we need to create this logical grid for ourselves that can hold some information for us. So let's take 10 minutes, right? So we're sitting at 2:37. We'll come back at 2:47, and then when we're done, I'll get a coffee or whatever, have a bathroom break. When we're done, we'll start building the grid. Okay? I'll stop recording now.